I do also want you to know there are 7 strong acids and technically there are 8 strong bases, and I would like you to memorize these. So memorize these and memorize these. So hydrochloric, hydrobromic, hydroiodic, nitric, chloric, sulfuric, and perchloric are strong acids. Your strong bases, these are pretty much your alkali metals, and these are a few of your alkaline earth metals. If you remember back to the Natanonics sheet, it said all your alkali metal hydroxides were strong, and then a few of your alkaline earth metals, so calcium, strontium, barium. So these are your strong bases. The reason you need to know those, they're going to completely break apart in water, and we say they ionize 100% ionize. And what that means is they're going to not get to equilibrium. They're going to break apart all the way. And so these problems with the strong acids and bases are actually a lot easier. Our next video we'll do weak acids, and then the video after that we'll do some weak bases. So they're going to break apart 100% as long as one of these strong acids or one strong bases. So we're going to do 5 different types of problems. 1, 2, and 3 are pretty easy. 4 and 5 get a little bit more complicated. All right. So it says, what is the pH of a 0.0256 molar hydrobromic acid solution? So hydrobromic acid is HBr, and HBr breaks apart all the way. If we were doing the in Gen Chem 1, we broke it apart and we did that and we labeled aqueous. Maybe you remember that, maybe you don't, but it breaks apart all the way. So what it means is that together it really doesn't exist. It exists only as broken apart. So if I were trying to write a reaction, I would kind of write this. I'm going to not put it plus the water. Well, I'm going to show you 2 ways to do it. So you could put plus water, single arrow because it's a strong strong acid, and what happens is that hydrogen comes off and makes hydronium ions, and you get the bromide ion, that is that conjugate base there. So this is one way to write it, or the other way to write it is simply, and I am a little bit on the lazy side, I do it this way. I just break it apart. Okay. So, but the point is, whether you like to write it this way or whether you like to write it this way, doesn't matter. These are the same thing. Is that this right here doesn't exist. After the reaction has finished, and it's not really a reaction, it's just a physical change, it's just breaking down in the water. But after it breaks down in the water, there is none of this. This doesn't exist. It's gone. Okay, so this doesn't exist. And water we don't care about because it's liquid. So it doesn't matter how much water is there. So what does exist, when it breaks down into an even ratio. So 0.0256 molar, and this is going to be a 0.0256 molar. A lot of students want to take this number and half it, which is interesting that they want to do this. It's saying that it's got this much of this combined thing. So because it's really broken apart, it's this much of this and this much of that. I don't know why this thing keeps spinning on me. But let me go to a blank page. Alright, I have a little drawing. No judgment on my drawing, okay? No judgment on my drawing. So if we had a couple and then they broke up, we have one boy and one girl, right? So, sorry, they're holding hands here and they broke up. What if I had 10 couples? Okay, so now there's 10 couples. When they break up, how many boys do you have and how many girls do you have? A lot of times students go, 5 girls and 5 boys. No, no, there are now 10 of these and 10 of these, right? Because they broke up. So now there's 10 boys and 10 girls. So that's how many there are of each one. So, so if we had in that example a 0.0256 molar solution, that's why they're equal amounts of those. So I'm hoping that makes sense to you. Okay, so now the reason I say that, it would work the same way underneath this. This is what I really need to know for calculating pH. To find the pH of this, I need the hydronium or the hydronium ions. So to find the pH, you simply take the negative log of 0.0256. Okay, because it's strong. If it was weak, you could not do that. Okay, I want to stress that. We're going to do weak in the next video. So in this video, they're strong, so I could have just taken the negative log of that. But I am going to make you write this reaction. This is the dissociation in water reaction. So I am going to make you write this out. So whether you write that one or that one, it doesn't matter to me. Okay, so I get 1.59. And the percent ionization, which is something else I'm going to ask on the test, because this is a strong acid, it's 100% ionized. What does that mean? It's in ions 100%. It's 100% broke apart is what that means. Okay, 100%, so it's strong. All right, that's a strong acid. Hard as that one gets. Now we're going to look at strong bases. The strong bases, I'm going to suggest that you don't put it in water. So you can on the acids, but for the bases, I'm going to suggest you just break it apart. So I'm just going to take lithium hydroxide. If you put it in water, it does give you lithium ions, and it gives you hydroxide ions. Okay, those are aqueous, both of them. But because this is strong, again, this doesn't exist. This right here doesn't exist. It's going to exist 100% in ion form. So when it breaks apart, you're going to get 0.00632 of this and 0.00632 of that. Which one do you need for pH? Well, honestly, you don't need either one for pH. There is no formula that has lithium. There is a formula that has hydroxide in it. So I could find the POH, because that's hydroxide, by taking the negative log of 0.00632 molar. And once I find the POH, and this comes out to be 2.20, then I could subtract it from 14 to get the pH, which is what it's asking me. It's a base, so it should be in the base region on the scale. So 2.2 wouldn't make sense. So it's 11.8. What's our percent ionization? 100%. 100% ion. All right. Look at this one. Strontium. Look, same thing. I mean, I've only changed one word in this. Strontium versus lithium. And the reason it's different is strontium is a 2+ charge. So when it works, when you make the formula, so when I write this reaction, you get SrOH2, and that's what's making this one different. When this thing breaks down, you get one strontium ion with a 2+ charge, but you only get one of them, and you get two hydroxides. Two hydroxides. So this is 0.00632 molar, but this is going to be 2 times that. It's going to be twice as much as that. So this is actually going to be, let's see, did I write that down? Oh goodness, I guess I did not. Oh yes, I did. So that is 0.01264 molar. Do you understand? That's going to be twice as much. Okay, it's twice as much because of that 2. So you're going to find that with that barium, that strontium, and that calcium. So why does that matter? Well, now this is the number that I need to find the POH. It's negative log of 0.01264 POH, and that comes out to be 1.90, and then the pH would be 14 minus that, which is 12.10. Alright, percent ionization, 100% ionized, because it is a strong base.